All right, so let's look and let's talk about linear regression and work through some examples together. You can copy down the information from the yellow packet on your own, work through that stuff. There's some videos I've got linked from Mr. Ben Schneider that walks through all of the notes for the yellow packet, but I figured what I would do for y'all is just work through the examples and talk about it. All right, so here we are talking about inference for linear regression, our last unit. Chapter 12, day 1, unit 7. Okay, so we have this situation where we're talking about constructing 70 long rotor helicopters from a model template, and then randomly assigning 14 of the helicopters to each of 5 drop heights, and we have the drop heights listed, right? And then we talk about having teams of students release the 70 helicopters in a predetermined random order, right? And work through all of that carry out, right? So we look to the information, and you're going to be able to find this reference on page 743 regarding this liner acronym, right? And here's what we have, right? Really and truly, you would never be asked, hey, use the liner acronym to check whether the conditions for performing inference about the regression model are met, right? You would just say, hey, are the conditions met? And liner is the acronym to check the conditions. There's a lot more conditions that you need to check when we're working with the inference for the slope of a regression line, right? So the first one, L, right? You need to make sure that your scatter plot shows a fairly linear form, right? And when we look over here at our scatter plot, the form is fairly linear, so we do meet that. I, we need to have independence. So that's going to be our 10% condition, unless we have an experiment. And in this case, with the random assignment of the treatments, we have an experiment. And so we have to make sure that there is no duplication and that we were released in a random order. And we do see that, hey, that we were released in a random order, so our condition I is met. N is normality. Our histogram of the residuals looks approximately normal. And if we look at the normal probability plot, also sometimes known as a QQ plot, right? And you don't really need to know that, but it's useful. So this normal probability plot for the residuals is fairly linear. So this lets us know that our residuals meet the normal condition, right? E is for equal variability, essentially. And we look at our scatter plot of our residuals, so right over here, right? We look at the scatter plot of the residuals, and we see that they are fairly equally distributed in terms of how much variability you have if we look across these, right? This one has a bit more, but it's not too far off from the others. And so we look that we have about fairly equal standard deviation of the residuals, so you could just say fairly equal variability of the residuals. Okay, and then finally the last one is R, and that is our random assignment. And in this case, the random assignment of the helicopters to the drop height. It wasn't simply the first ones that we made, we dropped from one height, the next ones that we made, we dropped from another height, but rather we did this work to be able to check to see, hey, I'm going to randomly assign to each of the 5 drop heights the helicopters rather than do it in some other prescribed order. So I need to meet those things. That's the acronym liner. That's a lot more that you need to check. But fortunately for you, you're not ever really going to have to draw it. It's just going to be like, hey, do you need to check, is this met? Yes, yes, it is. Okay. So once again, you can find more information on page 743. Okay. Now to the next part. Computer output from the regression is shown. Here's our computer output, right? You can see this example on page 748. Okay, and it says, give the standard error of the slope, SE sub B, and interpret this value in context, right? So remember, our linear regression is y hat equals A plus BX, right? The standard error comes from this where it says SE coefficient, right? So if I look at this, right, and I say, okay, well, my slope is not on my constant. My slope is based on this drop height, so my B value would be here. So there would be the standard error of my slope, okay? And then this over here, this T and this P, this has to do with the T statistic based on this slope and this standard error for that. But we won't worry about that right now, okay? So what's our interpretation? if we repeated the random assignment process many times, right? So if we repeated this process of randomly assigning these heights and these helicopters and these drop times, and or which one's going to drop first from what height, then the slope of the sample regression line would vary by that 0.0002 from the slope of the true regression line on average, right? So in other words, this is the variability in the particular slope that we find if we do this a lot of times. And that's going to be for predicting the flight time from the drop height. Remember, always have the context, right? So we say, hey, the slope of my sample regression line would vary by whatever that standard error is from the slope of the true regression line, and always add in the context. Okay, so that's the first part. There's a little bit more to this. Okay, so if we look at the next part of this question, right, got the next page, right, we show the regression output again, and we say find the critical value for a 95% confidence interval for the slope of the true regression line, and then calculate the confidence interval and show your work. Well, if I'm going to find that value, I'm going to be able to use my formulas, right? Here's the formulas. Hopefully you still have yours, right? You should have these formula sheets. Very, very important. And we look at this and we say, okay, well, the conditions for inference are met. We already checked that. The t interval for beta, the true slope of the regression line, is what we're looking for, right? So we still have to state what interval are we doing, and it's going to be a t interval, not for mu now, but it's going to be for beta, the true slope. Our degrees of freedom is going to be n minus 2. No longer is it n minus 1, and that's because we're using two different values to make our calculations. We have A and B, right? So we have to subtract those two, right? And we have 68, right? Now, if I'm going to use a table, my degrees of freedom would be 60. Why would it be 60? Well, I would come over here to my table and I'd say, okay, hey, 68, oh, 68 doesn't show up on my table. So I'm going to have to be more conservative and go with 60. A 95% confidence level at 60 gives me 2.000. Okay. And so that's where the 2.000 comes from. If I was going to do this work with a calculator, well, then that value that I would get would be 1.995. Sorry, I'm over here trying to see if I could find the calculator. I don't have it right on me right now. So we'll just go through this work. I was going to show you how to do it with the calculator, but you should be pretty good with that by now. All right, it would be inverse t in this case. So our interval is going to be b plus or minus t star se sub b, which is our statistic plus or minus our critical value times the standard error of our statistic. All right. So here we found the slope, the 0.005724 plus or minus the critical value, and then the standard error. If I do that, put it in my calculator, these are the values that I get. With my calculator, if I was going to be doing a t interval, right? If I was going to be doing a t interval, with my calculator, these would be the values that I get. And then let's interpret that interval. Right? Same as always, same things, repeated. So we are 95% confidence that the true slope of the regression line relating flight time and drop height of the paper helicopters like those used is between 0.03218 and 0.0061270 seconds per centimeter. Okay, so all the things the same, but always remember you have to talk about the context. So what's the population, right? Helicopters like what we're using. And what's the context? Well, the flight time as related to the drop height. So the time in seconds per centimeters for the drop height. Okay, and then finally, right, explain the meaning of 95% confident in context. Well, what's going to be that meaning? It's going to be that if we repeat our experiment many times and we build our confidence intervals in a similar fashion each time, then about 95% of the resulting intervals will capture the true slope of the regression line. relating flight time to drop height. Once again, always include your context, right? So repeat this many times, build the intervals each time. About 95% of those intervals will actually capture the true, in this case, slope of the regression line. All right, so that's this first situation. Hopefully everything's well understood for you. All right. Otherwise, if you have questions, make sure that you call and, oh, sorry, you really can't call, you Zoom, right? Or that you send an email. Okay.